This video shows you how to use the Deep Network Designer app to perform transfer learning. Transfer learning is the process of adapting a pre-trained network to a new task. Fine-tuning a network using transfer learning is usually much faster and easier than training a network from scratch. To begin, load a dataset into the workspace. This example uses images of MathWorks merchandise in a folder called Merch Data. To perform transfer learning using Deep Network Designer, open the app by selecting it from the Apps gallery. Deep Network Designer provides several pre-trained networks for image classification problems. You can use any of these networks for transfer learning. For this example, choose SqueezeNet. When you import a network, Deep Network Designer displays a zoomed-out view of the network architecture. From this view, you can see the properties of the network. For example, SqueezeNet has 68 layers. Zoom in to take a closer look at the layers. Select a layer to view its properties. For example, you can see that the image input layer requires an input image size of 227 by 227 pixels. To load the merch data into Deep Network Designer, select the Data tab. Click Import Data and then choose Import Image Data. In this dialog box, you can select your training data, set augmentation options, and choose validation data. First, select the unzipped merch data as the data source. The names of the subfolders are used as the class labels for the images. Next, specify the augmentation options to use during training. Data augmentation helps stop the network from overfitting by preventing it from memorizing the exact details of the training images. In this case, apply a random reflection in the x-axis, a random rotation between -90 and +90 degrees, and a random rescaling factor of between 1 and 2. Validation data allows you to track how the network is performing during training. In this example, keep the default settings. This means that 30% of the data is used for validation. Import the data into Deep Network Designer. The data pane shows a histogram of the class labels of your data. You can see that this dataset has 5 classes. Next, adapt the pre-trained network to work with your data. Scroll to the last learnable layer. For this network, this is the final convolutional layer. Click and drag a new convolutional layer onto the canvas. To match the current convolutional layer, use a filter size of 1 by 1. Change the number of filters to 5 to match the number of classes in your data. Finally, to learn faster in the new layer, change the learning rate of the weights and bias to 10. Delete the previous convolutional layer and connect your new layer instead. You also need to change the final output layer so that it can automatically adapt to the new data. Click and drag a new classification layer onto the canvas. Delete the original output layer and connect your new layer instead. Arrange the layers automatically. Analyze your network to check that the network is defined correctly and there are no problems before training. Confirm that the Deep Learning Network Analyzer shows no errors. Once you have imported your data and prepared your network for transfer learning, you can train the network. First, set your training options. Set the initial learning rate to a small value to slow down learning in the transferred layers. Earlier, you increased the learning rate factors to speed up learning in the new layers. This combination of learning rate settings results in slow learning in the original layers and fast learning only in the new layers. Set the validation frequency to 5 and the maximum number of epochs to 8. Because the data has 55 observations, set the mini-batch size to 11 to divide the training data evenly and ensure the whole training data set is used during each epoch. You're now ready to train your network. Deep Network Designer copies the network for training. The app also automatically resizes and normalizes the imported data so it matches the input size of the network. During training, Deep Network Designer displays a training plot showing the accuracy and loss. The accuracy and loss lines of the validation data appear as black dashed lines. Monitoring these curves is important for diagnosing overfitting or underfitting. Training is now complete. You can now use this network to classify images of MathWorks merchandise. You can generate Matlab code to recreate the building and training of the network. You can examine the generated code to learn how to perform transfer learning programmatically. To use the network in Matlab, export the trained network and results to the workspace. Test the network performance by classifying a test image. This test image was not part of the training data, so the network has not seen this image before. You can see that the trained network correctly classifies the image as a MathWorks cube with high probability.